Prescott. This work was done at the University of North Florida in collaboration with the University of Tennessee at Knoxville and Oak Ridge National Laboratory. So today we're going to look at probing intermolecular magnetic interactions in metal complexes by using inelastic neutron scattering. So the first question is, why do we care about these materials? And we're looking at magnetic molecular solids, which are molecule-based magnetic solids held together by van der Waals forces and dipole-dipole interactions. When these molecular materials have magnetic centers, they make for some really interesting applications, such as nanoscale spintronic devices, magnetic switches, sensors, spin valves, logic gates, and devices for memory storage. So in particular, the samples that we'll be looking at are porphyrin compounds, and specifically we'll be looking at metalloporphyrin compounds, which are a class of porphyrin compounds that have a metal center. And in particular, we are going to be looking at those that have a magnetic center of manganese and iron. So here are the crystal structures and molecular structures of the compounds that we'll be investigating. On the left here, we have iron, our iron center metaporphyrin compound, which has a iron 3+ ionic center and a total spin of 5 halves. On the right, you'll see the manganese centered sample, which has a manganese 3+ center with a total spin of 2. And you'll notice the distances between magnetic centers are strikingly similar between the two compounds, with vertical distances of 9.68 and 9.86 for manganese and iron, and distances of 13.48 and 13.46 between magnetic centers on the base and side for manganese and iron. So now that we know the samples and a little bit about them, I want to look at the energy transfer data by neutron scattering. So we start by looking at the manganese center, and we see our first peak pop up around 2 wave numbers, and we see our second peak around 7 wave numbers pop up. And this lines up with what we expect theoretically, and our main excitations happens at the around the 7 wave number line. And then for iron, we also see what we expect, a very small excitation around 6 wave numbers or so, and then a larger excitation around 12 wave numbers. The interesting thing about the iron, however, is that we look at the peak and we see that there's some sort of shoulder off to the left. So this is interesting to us because all the other excitations, it is just a straight peak and there's no sort of perturbation. So we investigate closer and zoom in on the energy scan, and we see that there's a distinct shoulder and what looks like 2 excitations on top of one another. So now the question is, we know there's an ionic excitation. What is the other excitation? We suggest that there is a cluster-like interaction or some sort of spin exchange interaction happening next to the single ion excitation. And when fitting the energy transfer data, we get this smaller blue peak representative of our exchange interaction, and then the larger pink peak as our single ion excitation. So now we look at the Q dependence of our neutron scattering data to see if there's any telling nature of exchange interaction. And typically in exchange interactions, we'll see some sort of oscillation within the data. And for a single ion, it will just typically go straight down and follow the data in a line downwards. So we look at the iron and we see something reminiscent of oscillations near the midst of the data, but mostly we see single ion. This kind of makes sense as we see a slight oscillation and the exchange peak from our energy data is shifted off to the side. However, when we look at our manganese sample, we see a clear oscillation within the realm of error. And this is curious to us because we see no shoulder or nothing indicative of an exchange interaction in the energy transfer data. Therefore, we suggest that the exchange peak must be underneath the main single ion peak. Now, how does this effective exchange happen physically within the model? We introduce what we call the effective exchange model, where around our magnetic center, there's an effective magnetic field due to all the other surrounding centers. And the transition metal center interacts with the effective field in a cluster-like interaction. So this gives us bounds to claim intramolecular interaction between magnetic centers and allows for us to parameterize and get distinct values for each sample. And in modeling each sample, we model the cross-section or the Q dependence of the data. And we start by using a dipole approximation, which takes out the complexity of the geometry of electronic orbitals, simplifies them to spherical, which in our case is a fine approximation to make due to how the orbitals are filled in both of our samples. So we use that to get our magnetic form factor F, which will tell us the amplitude of the scattering. And then we use that and split it to a single ion and effective exchange interaction. So you see here, we have a lowercase f in red, which would just be the single ion. And then we have a 1 minus a lowercase f in blue times this exchange interaction equation for a dimer. And that will tell us how much dimer or how much cluster rather, and how much single ion interaction there is within our sample. This R parameter here is telling of distance between magnetic centers. And this C sub 1 is the dimer matrix element multiplied by some percentage. These two A and B terms just account for any background noise within the experiment. And this C sub 0 will just scale our model to fit the data. So now we fit the data with our effective exchange model, along with another model supposed that uses a average over the distances within the crystal structure. So in the top row of each row section of the parameter, we have the effective field, which is our model, and then below is the average field, which is the other supposed model. And what we find is quite interesting in that the only model that can follow the oscillatory nature of the Q dependence data is the effective exchange model. And in the iron data, we see that it starts slightly out of phase in the beginning and then captures the oscillations near the end. Whereas with the manganese data, we find that there's a clear agreement and it follows the oscillation in phase and seemingly at the proper amplitude, along with the fact that it gives us nice parameters of our matrix elements coming out to be almost exactly that of a spin 5 halves dimer for iron and a spin 2 dimer for manganese. And we get intramolecular distances of 11.84 angstroms for iron and 13.22 angstroms for manganese, which is all within bound of the crystal structure of these molecules. And furthermore, when we look at the fractional percentage, we find that with iron, we see mainly an ionic excitation, which makes sense since our exchange peak is shifted off to the side. And with manganese, we see about a 50-50 ion exchange interaction, which also makes sense considering we would have an ionic peak right on top of an exchange peak. So to conclude, our effective field model shows great agreement with the data. And when it comes to modeling the oscillatory Q dependence, we show that there are intramolecular interactions within the structure. And furthermore, I think that this experiment could be built upon with different samples and varying incident energies and temperatures for each sample taken. And I'd like to acknowledge those who